In this video, we shall see the main electrical components that are present in all power electronics used to convert direct current and alternating current. These components are four: the switch, the inductor, the flyback diode, and lastly the smoothing capacitor. Then, once we understand how these components work, in the next video we shall deploy them in various topologies. First of all, we need switches, which are designed to turn on and off rapidly from 10 to hundreds of kilohertz, in order to be quick enough, but also not too fast, to decrease eventually high-frequency harmonic distortion. Traditionally, thyristors, such as gate turn-off thyristors, were used as switches, and basically it is an electronic component consisting of PN-PN layers, and thus it contains 3 PN junctions. One disadvantage is that thyristors cannot be turned off, but only turned on. Such switches lead then to a very high harmonic content, requiring additional filters in order to make the output compatible with the electricity grid. Nowadays, thyristors are only used for inverters with a power of 100 kilowatts and above. Indeed, there exist also other types of switches that generate an output with very little harmonic content and that are fully controllable. The most popular technologies are insulated gate bipolar transistors, or IGBTs, and metal oxide semiconductor field effect transistors, or MOSFETs. So when you have to design a new inverter or a converter, it is better to see what are the properties of each switch in order to make the most out of them. In fact, the best choice is a trade-off between fast operations and the energy losses, which can be easily calculated for each type of technology. The next component is the inductor. Simply speaking, the inductor is a lumped electromagnet that serves to store energy in the form of a magnetic field. To understand how an inductor works in a circuit, we will use the following example. Here we will have a battery or a power supply, a light bulb, and a switch. In this simple circuit, if you close the switch, then the bulb lights up as expected. However, when we place a coil of wire, which represents the inductor, in parallel to the light source, the circuit's behavior is completely different. First, note that the light bulb is basically a resistor, and this resistance creates heat to make the filament in the bulb to glow. Also, the wire in the coil has a resistance, but it is much lower than that of the light bulb. When we now close the switch, the bulb burns brightly and then gets dimmer. That is because at the beginning, less current flows in the coil, which is building up a magnetic field resulting in a repulsive electromotive force, depicted here in orange. While the field is building up, the coil inhibits the flow of current, but after a certain amount of time, the energy is stored in the magnetic field and the current can flow normally through the wire. Then, opening the switch, what happens is that the bulb burns very brightly and then quickly goes out. The reason is again the inductor. Indeed, the magnetic field around the coil keeps current flowing in the coil until the field collapses, and this current keeps the bulb lit for a period of time, even though the switch is open. In other words, the inductor stores energy in its magnetic field, and it tends to resist any change in the amount of current flowing through it. This type of behavior is given by this first-order differential equation, where the voltage across the inductor is proportional to the derivative in time of the current that flows in the coil, and by calculating this current, it is also possible to calculate how much magnetic energy is stored into the coil. The second component that we introduce is the flyback diode, extremely important for the converters. It is a diode used to eliminate flyback, which is the sudden voltage spike seen across an inductive load, happening when its supply current is suddenly reduced or interrupted. Let's see this problem in details. In its most simplified form, there is a voltage source connected to an inductor with a switch. In a steady state, with the switch closed, the inductor has become fully energized and it is behaving as a short circuit with the current flowing down from the positive terminal to the negative through the inductor. However, in the moment that we open the switch, the inductor will attempt to resist the sudden drop of current by using its stored magnetic field energy to create its own voltage. Hence, an extremely large negative potential is created across the inductor, and the voltage at the switch becomes the sum of the voltage of the power supply and the voltage of the inductor, generating a very large potential difference that can cause electrons to arc across the air gap of the open switch. Problems might occur when the switch is very fast, so you have in a very tiny amount of time that the derivative of current becomes very high. This can be potentially dangerous, since if there is necessary environmental conditions are met, you could even have a spark. A flyback diode solves this starvation arc problem by replacing it in parallel with the inductor. When the switch is closed, the diode is reverse biased against the power supply and does not exist in the circuit for practical purposes. However, when the switch is opened, the diode becomes forward biased relative to the inductor, allowing it to conduct current in a circular loop, so the current that was charged inside the inductor can still circulate in this topology without being eventually transferred to the air with an arc. So this is the concept of a flyback diode, which is activated every time an inductive load is switched off. And finally, another important component is the smoothing capacitor, which is placed in parallel with the load. From all these switches, the resulting signal is periodic in time, but actually the output of a DC-DC converter has to also be a DC signal. So the solution is to place a smoothing capacitor, also called reservoir capacitor, to smooth the signal. As the voltage of the signal increases, it charges the capacitor and also supplies current to the load. When it reaches the peak of the signal, the capacitor is charged to its peak value, and here the role of capacitor is evident because it starts to release the stored energy. So in this short gap of time, the continuous flow of current gradually moves to the next periodic pulse, filling the gap and allowing the load to be powered at all times without any interruption. To conclude this video, we have seen three different types of switches, then how an inductor works, and the importance to use a flyback diode to avoid the voltage spike seen across the switch when we open the circuit. Lastly, we also introduced the smooth capacitor, which attenuates the signal periodicity. In the next video, we are ready to see the first topology of a DC-DC converter, which is the buck converter.